Hello and thank you for joining us for today's webinar, Chatter Less, Work More, presented by Aviation Week Network and sponsored by Makino. I'm Sean Broderick with Aviation Week, and I will serve as your moderator today. In this webinar, we have our sights set on the confusion around vibration and chatter, which have long been the most misunderstood realities in the machining world. Since chatter can result in scrap parts, broken tools, and even severe machine damage, it remains a common topic of conversation among machinists and engineers. However, the result has been continued confusion and rules of thumb that often don't work. In this webinar, you will learn about the causes of chatter, how to best avoid chatter while still maximizing metal removal rates, and measurement techniques associated with identifying and correcting chatter. We will discuss how these advancements are helping companies meet their goals and conform to their specifications. Before we begin, a few words about this webinar technology. This platform allows our audience to be more involved with the presentation and, more importantly, allows you to watch this event the way you want to watch it. To begin, feel free to customize your webcast console. You can move windows around by dragging on the title bar or resize your windows by clicking on the lower right corner of any window. You will notice a toolbar at the bottom of your console. These buttons allow you to open and close widgets on your screen. And by the way, we invite you to get social. If at any time during our session today you hear something interesting, feel free to tweet it to your followers using the Twitter widget. If at any time you experience difficulties with the audio or advancing of the slides, simply press your F5 key to refresh your webinar console. Once again, F5 refreshes your console. And for all you Mac users out there, that is Command R. You can download the slides for this webinar by clicking on the folder icon on your screen. You can do this during the webinar. It will not interrupt the presentation. We appreciate your feedback, so please click on the red survey icon and complete the form. Now I'd like to introduce today's presenters. Dr. Andrew Honeycutt is a senior research and development engineer at Makino. He came to Makino after earning his PhD at the University of North Carolina, Charlotte, which is renowned around the world for its expertise in the science of machining. Andrew specialized in the study of machining dynamics and participated in the publication of several papers, including Fixed-Free Beam Dynamics Prediction for Thin Rib Machining and Productivity Progression with Tool Wear in Titanium Milling. We will also be joined by Brian List. Brian joined Makino in 2003 and quickly became engaged in the intricacies of machining technology, traveling the world supporting projects for a number of high-production automotive, medical, and small arms parts. Promoted to the role of process development engineer, Brian was charged with the task of understanding and overcoming the challenges of machining hard metals, specifically titanium. Bringing together his practical experience with customers and his R&D experience in the lab, Brian then worked as the competitive intelligence manager. He most recently made his way back home to R&D, where he serves as the team leader for research and development. With that, let us begin today's webinar. Gentlemen?
Thank you very much, Sean, for that introduction. We are here to talk about chatter in your work and how we can overcome the challenges involved with machining parts. I want to give a quick review or understanding of some of the types of graphs you're going to see and some of the challenges we're facing. To get us kind of aligned with the type of information you're going to see during the next hour here, this is a chart that came out of a dynamometer measurement. A dynamometer is a machine that, or a device that allows us to measure cutting forces in different directions. So we mount this up on a tombstone or on a table. We take a machining path, and we can get these cutting forces out. And we want to talk about the foundation of where chatter comes from. But first we have to understand what kind of information we can get and understand with these devices, and understand that nothing really is completely even. When you see a smooth cut on a machine, we actually get something that looks a bit like this. And if you look at the blue line here, we've got the x-axis measurements, and we can see some variation there. It's going to come from our runouts or our tooth pass frequency. But this is generally a stable cut. And we see on the x-axis that's about 2 kilonewtons on the x, and on the red line there we're running about 5 kilonewtons. And what happens when we get a chatter situation is that same cut, that same engagement, the same average cutting force actually creates, we get a wide variation in the loads. So if you look at that blue line, this is the same average force, but we're spiking up to 5 kilonewtons and down to 0. On the y-axis, the red line, we're going down to 10 kilonewtons and up even past 0 again. So we're getting these huge variations in forces, spiking very, very high, which is generally what's going to result in chipping our tools or damaging our machines or our workpieces. So because of that severity and difference in cutting forces we get when we encounter a chatter situation, it's really important that we understand that. And throughout this webinar today, we're going to talk about what is chatter, some of the rules of thumb that people have used to try and overcome the challenges and whether or not those are actually true, how you can measure it, and what you can do to make your processes more productive and more profitable. So with that idea in mind, I'm going to now introduce or hand off to Dr. Honeycutt, Andrew, who's going to give us the first thing we need to do in order to start understanding chatter.
Thanks, Brian. The first step is you need to unlearn what you've learned. And this is kind of a joke. We're not saying throw everything out the window. But there's a few things that we are going to describe, and they are, I would say, maybe a little inconsistent with people's understanding. So we want to say, hey, let's try to start from a blank page and work our way up to an understanding of what chatter is instead of trying to conform to the current lingo or terminology that's used out in industry to kind of give hand-wavy explanations for what chatter is. So it was just a joke to try to lighten it.
Yeah. And one of the first things we talked about was, or you've identified within the machine world, is this word rigid. It gets thrown about a lot. And in fact, you were telling me that there is no such thing as a rigid item, right?
Correct. So the term rigid came from our undergraduate engineering or physics background, and it was used to describe an object that does not deform or deflect under a load. And there is no such material, no such object in this world that fits that description. Yeah. So it's this idealized thing that we came up with to help simplify some problems so that we can come up with a useful, solution. So in this beam bending example, they always said, this looks hopefully familiar from your undergraduate courses, that when you push on the end of that beam with a force F, the beam is going to deflect. And one of the things they described as those hash marks on the left side is a rigid connection. So what that means is that thing's not deforming or deflecting the wall that's connected to the beam. Only the beam itself is deflecting.
Right. And then for most of us, just calculating the deflection, understanding what's going on in that beam was complicated enough.
Yeah.
So we were very happy to assume that the wall was rigid, but in fact that is not the case, and there's nothing in our world. Everything's moving around, everything's vibrating.
Yes.
It's very important in our world. So in a machine situation, chatter comes from when we have this motion, which is always there. Whether we are calling it chatter or not, whether we're saying it's a stable or unstable process, we always have motion, there's always vibration.
Yeah.
But the chatter is when it's essentially harmful, typically something you hear that's real loud. So that's what we're going to be talking about trying to overcome today.
Yes.
And so we go our next graphic here. You have another dynamometer, another force measurement.
Yes.
Which I think is just incredible. This x-axis you're showing me is half a second.
Half a second.
All of this data was gathered in half a second. And each of these humps is 1/2 of a cutter entering a workpiece. Is that right?
Yes.
So you have, you were saying, like 30 different
tooth
passages on this. And in this case, the feed per tooth was about 0.19 millimeters, which is just under 0.008 of an inch. And so this is generating these cutting forces. In this case, we can generally assume that the cutting forces come from the chip thickness, right?
Oh, yes.
And
sure.
So we definitely assume that as you create a thinner and thinner chip, the cutting forces would go down.
You would think, yes.
Yeah, but you had this situation where you ran the same test, and then you ran it at half a thou, so we're going to show that now. At half a thou for tooth, 12 microns, and we get this mess of data, and the cutting forces are going much, much higher than what we have below, but only like 5 to 7% of the productivity. We're cutting. So how is this possible? How could you be getting so much force when taking off so much or so little material?
So when the feed per tooth values, you'd think, as you said, it seems like it would be intuitive to suggest that you decrease your feed, it's always going to decrease your forces. What happens though is when you decrease your feed per tooth too much, you're not able to effectively shear the workpiece or shear off a chip. Because that feed per tooth is so low, you can actually deform the material, elastically deform the material, or unpermanently, that's another word for elastic, it will return back to its original position, and not shear off a chip. You can elastically deform your workpiece if you have a small enough feed per tooth, so that after that tooth finishes trying to shear away a chip, you haven't done anything.
It's just rubbed on the material.
It's just rubbed on the material.
Yeah.
And what can happen is, let's say one tooth fails to shear a chip, it only rubs, and let's say the second tooth fails to shear off a chip, and it just rubs. Well, now the third tooth has to take 3 times the expected cut because the first 2 didn't cut anything. So you can see where you have a miss cut. And even in the best case scenario, if that pattern followed, you would have erratic behavior because it's not saying tooth passage, force, tooth passage, force. It's saying rubbing, nothing, oh, we sheared a chip, oh, rubbing, nothing. And that, that in the top graph, everything is held the same except the feed per tooth is changed.
Yeah.
And you see erratic and unpredictable and also higher cutting forces than you do with tool, the tool when it's fed at an appropriate amount.
Yeah, so there's probably some noise and squealing that occurs.
It sounds awful, yeah.
And so that's quite fascinating. So this is one type of chatter you get.
Yeah.
You'd actually use the illustration of like trying to cut Jell-O.
Yeah. So for this example, I like to use or to visualize, a block of Jell-O, right? And if you've got a knife and you try to cut off a 1 millimeter thick slice of Jell-O, not going to happen.
Yeah.
The Jell-O is either going to deform and push your knife off to the side, or your knife is going to slip more into the Jell-O, and you're going to cut, a 5 or 6 millimeter cut of Jell-O. And when you're trying to cut such a thin slice, you can't ensure that you're going to create a chip. There can be some elastic deformation that pushes the tool to the side or pushes the workpiece to the side, which results in a failed chip, if you will.
Yeah. So while this is an important thing to understand and can help get some machinists and manufacturers out of a sticky situation if you're perhaps having this rubbing occur at a low chip load, it is in fact not the type of chatter we're going to talk about today.
Correct.
So don't want to mislead you, but that is one that comes up. It is considered chatter. Today we're going to be talking about more along the lines of natural frequency, right? And for those of our viewers out there, the next few minutes we're going to give you something this is the most important part.
Yes.
It is the meat of understanding chatter. And so we're going to give you this, and then we're going to give you some rules of thumb and help you evaluate based on this understanding whether you agree with those rules of thumb or not. So stay tuned here. Andrew's going to walk us through this diagram and help us to understand what is what do you call it, natural frequency chatter or.
So we love fancy names for things, so we're going to give this a fancy name, and it's referred to as regeneration of waviness or regenerative chatter sometimes. So there's more. It's once you get into the nitty gritty, chatter is a broad term used to describe any unstable machining process, and the type of chatter that we're going to discuss is the regeneration of waviness.
Generation of waviness.
Right. So regeneration is it'll make more sense when we draw when we bring up the next diagrams. But for now, just let's think of it as a difference. So in this type of chatter, your previous tooth passage sheared off a chip and created a surface. That's the right side of that red chip that we have there.
No.
And then you're going to feed your tooth, advance it, the feed per tooth, and then your next tooth is going to try to shear off the left side of that chip, right?
No. And if everything was stiff, really perfectly rigid.
Right.
We can't use that word.
Right.
It would be something like that.
Exactly. and that's kind of the mental image that is not easy, that I find a lot of people have. That tool, because you can't see it moving, it's not moving. But it is moving, it is vibrating, nothing is rigid. So, that chip is the idealized chip, right? If it was a rigid tool, almost circular tool path, you get a chip that looks like that. But what's actually happening is the tool is vibrating and the tool is rotating.
Yeah.
So it can vibrate in all directions, but let's simplify for this example to understand this. Let's pretend that it can only vibrate in the direction shown, that it can only vibrate back and forth with the tool vibration arrow there. So it's only vibrating back and forth and it's rotating. So if you try to combine those two motions in your head and picture what the chip might look like, you wouldn't have that perfectly crescent-shaped chip. You'd have waves on each side of that chip. So we've shown up here a chip. The black chip would be the nominal chip that we formed. Idealized, exactly. And then the red would be what happens if your tool's vibrating while it's rotating. So it's going to vibrate to the left, and it's going to cut off more than the idealized chip, and then it's going to vibrate back to the right and cut off less. And so this picture is, at least, we've exaggerated it greatly, obviously, but this helps us picture what's going on. So it's not forming this idealized black chip. It is vibrating and rotating, and it's forming the red chip.
Right.
And what's happened in this example is we have inconsistent chip thickness because the spindle speed and the tool vibration are out of sync.
Yeah.
And what that means is every time the next tooth passes, because the tool vibration and the tool rotation are not in sync, you're going to get phasing of those two surfaces, or you're going to get varying chip thickness across the idealized chip thickness. So in this one, it happens to be the worst case scenario because those two waves line up in such a way that we have a huge chip thickness there as we start the cut, and then as we work our way down through the cut, it goes to a very, very, very small chip thickness there in the middle, and then goes back to a large chip thickness as you would be exiting the cut for this down milling or climb milling example.
Yeah, and you mentioned a couple slides ago that the cutting forces are directly proportional to your chip thickness.
Yes.
So normally we have this thick to thin, but here you've got this variation. So now we can start picturing in our mind why the cutting forces start to fly all over the place.
Yes.
And spike up and down.
Exactly.
We're taking twice as much thickness, perhaps, in some cases.
Right.
Worse.
So what's important to lock into your head is there's no such thing as this idealized chip that we've drawn here. It's nice because it helps us understand at the beginning. Yeah. There's no such thing. That tool is always vibrating.
Yeah.
Now, if it's stable, its vibration can be more easily described using simpler methods. But when it's chattering, you're not very sure what's going on, right?
Yeah.
So, but the important thing is to realize that the chip thickness is never going to be this perfect, idealized thing that we have. There's going to be waviness in it. What we can do, though, is if we select good spindle speeds, we can actually get what we have on the left there, which is a consistent chip thickness across. So I drew the black chip to be the idealized chip, just so that we have some reference. And then the red chip would represent a consistent chip thickness. And you say, well, that's wavy. What do you mean by consistent? It's consistently thick, though. When you follow it from the beginning of the cut to the end of the cut, it still follows the same pattern that you would with the idealized or the nominal chip. So at the beginning, from the previously cut surface, the thickness as you follow that wavy chip down is at least consistently wavy, if we can say that.
Yeah, the cross section is following that thick to thin pattern, so you're getting this predictable, smooth transition in the cutting forces.
Yes.
Now, what's interesting here is on the left, you've done something with the RPM to get those two frequencies to match, right?
Yes.
And so you're going to walk us through now. If you know the frequency that your tool is vibrating at, you can adjust the RPM,
right,
and get this in line. And in fact, we were talking that this is what you've seen machinists do for years, right? As someone who, you can hear it when it's bad, and they can adjust the RPM.
Yes.
And what I find really interesting about that, and what I hope the viewers picked up on this, is that you are actually matching these vibrations when you use the spindle speed selector to settle down chatter.
Yes.
You're looking for what RPM gets these waveforms in line.
Yes.
So that we have a consistent in sync vibration. And what I find so interesting is that I think of the classic situation of the opera singer resonating the wine glass till it breaks.
Yeah.
And in that case, their voice is producing a frequency that matches the natural frequency of the glass.
Right.
And that's very bad. So I always thought for a long time that matching the natural frequency of the tool would destroy the tool.
Right.
But in this particular case, matching these frequencies helps to settle down the cutting forces.
Yes, it leads to it doesn't settle them down in that it lowers the forces, but it leads to a more consistent force from chip to chip. And the more consistently you can excite your cutter, the more material you're able to remove stably. So it's getting the same thing every time instead of these erratic changes from chip to chip.
Okay. So if we want to match that RPM, I'll let you walk us through that process. Now, how do we think about that in terms of these frequencies that we're dealing with?
Right. So one half of that equation is we need to know what frequencies the tool vibrates at. We're going to talk about that later.
Yeah. Let's
figure out how to relate our spindle RPM to what we're going to call the tooth passing frequency.
Yeah.
And those are the two things that you want to line up, because if your tooth passing frequency is near the tool's natural frequency, that's the best cutting force. And that's going to lead to that consistently wavy chip.
Yeah, and that's the second big sciencey term you throw out. We've got regeneration of waviness, we talked about, and then we've got tooth passing frequency.
Right.
I think as you walk through this, that'll make more sense.
Yeah, so this example shows us how to calculate a tooth passing frequency. And so let's say we've got this 3-flue cutter rotating at 900 revolutions per minute. That is 900 revolutions per minute times 3, let's call them hits per revolution.
Okay. Yeah.
Chips per revolution, whatever you'd like to call it. But 3 times is generating a force that goes from high to low.
Yeah.
So 900 times 3 is 2,700 hits per minute. And in the frequency world, we typically describe vibrations in hertz or cycles per second. So we have right now 2,700 hits per minute. We want to turn that into hits per second.
Mm-hmm.
So we would just divide by 60, and then that gives us 45 hits per per second, or 45 chips per second, or 45 hertz. That would be the tooth passing frequency.
So we're getting a variation in a stable cut, even so. You're getting a variation in cutting forces, and that variation is going to have a frequency of 45 hertz.
Yes.
So we predict.
Yes.
Then we've got the other side of this, tool vibration. How do we get that? How do we know what the tool vibrates?
So that's difficult. And one of the methods that is probably, I would say the most popular, is to use impact testing. Sounds a little aggressive. Maybe I've also heard it called tap testing as well. Modal testing, modal analysis. There's a lot of words that can describe it. I'm just trying to throw these out there in case somebody has heard of it and they're like, oh yeah, okay, that's the whatever.
Not trying to sound impressive.
No, not at all. So with this kit, this is a Metal Max kit, and it has all the stuff that you need to measure a tool's frequency. So there's a hammer up at the top. You can sort of see it. It's got the black handle and then the gray metal top and then that little white tip on the end of it. And when we're trying to figure out what frequencies, what are the tool's natural frequencies, this method, what it does, is it lets us excite the tool or hit it. And that's an instrumented hammer, so it measures the force with which we excited or hit the tool. Yeah. And we're not talking about destructive hitting. These are, taps.
You're just not giving a little knock.
Correct.
With a nylon tip to send it into a vibration.
Correct. We want to somehow input energy into that system, which is one half of it. Yeah. Then the other half is we got to see what the system did, and by system I mean tool, what the tool did after you hit it. We'll use an accelerometer, which is a device that will measure the acceleration. So we attach the accelerometer to the tool so that the accelerometer moves with the tool. So as the tool vibrates, so does the accelerometer. And that accelerometer gives us the information we need to determine what the tool's natural frequencies are. So because we know how much we excited the tool, and we measured what the tool did after we excited it, we can extract useful information about the tool's natural frequency.
Yeah.
Now, for most of us out there, we couldn't care less what the tool's natural frequency is as a number.
Right.
Nobody. You go to the shop manager, the production manager, and you say, "Are you very interested in what the tool's natural frequency is?" And he's going to say, "No, I couldn't care less." So what the software also does is it takes that information, puts it in a useful way. So by knowing the tool's natural frequencies and how it behaves under certain conditions, you can create this graph that's shown in the bottom right-hand corner. And again, with the fancy names, I'm sorry, that's referred to as a stability diagram or a stability lobe diagram. And the way that this diagram works is it tells us the different combinations. So the horizontal axis is spindle speed and RPM, and the stable depth of cut is the y-axis, and it gives us the roadmap essentially of where we could machine stably and where we would machine in chatter.
Yeah.
So if you pick, let's pick a 6,400 RPM and 2.5 millimeter depth of cut. The point would be in the red zone of that stability lobe diagram. That would be bad.
Right,
we don't want to cut and chatter, right?
It would predict failure.
Chatter at least, yeah. But if we made that same cut at 6,400 RPM at 0.3 millimeter depth of cut, it's in the white section.
Yeah.
So that represents stable cut. So that's how you interpret this graph right here. Red is bad or chatter. White is a good stable cut.
I find there's actually a lot of interesting information in these for those who haven't seen this before. I would have thought it should be called the instability lobe diagram because the red part, the lobes, are the unstable area. But you notice as you get into higher RPMs, these sections of stability get bigger and bigger.
Yes.
So higher RPM machines, this is really, really valuable when you're cutting aluminum at higher RPMs.
Yes.
You can find a great RPM and a great axial depth.
Yes.
What I also found very interesting is you notice there's like this line where all the loads don't go below it, right? So there's this level on this particular graph around 0.3 where it's saying everything's stable.
Yes.
You're just not putting in enough energy.
Correct.
To cause it to negatively start chattering. So that's one thing you can always take back. If you are in a chatter situation, there is a point where eventually you can get back in this thing off.
Correct.
And as long as you're not getting that condition we had at the beginning where you're creating really low chip thickness and rubbing,
right,
it's going to be stable. So you can at least survive a cut if you have to at that.
Yes.
But we would like to find something more productive than that.
Yeah. Well, the information that we want to give to the viewers is, yes, we want to avoid chatter, but the plant manager also wants parts out the door.
Yeah.
So avoiding chatter is just one half. You got to make a good part, right? So if you're chattering, you can't make a good part typically. Okay, if you reduce it to that lower limit, yes, you're making all good parts, but you haven't increased your efficiency or your material removal rate.
Yeah.
You've just created a good part. We want people making good parts faster.
Yeah.
And this tool is what helps you achieve that. And it's not something you can just know. You can't look at a half-inch tool and say, oh, yep, that one's at 712 RPM or 14,002 RPM or anything like that. You need measurement equipment to be able to understand how your tool behaves. Once you know how your tool behaves, you know how you can use that tool to its fullest potential.
Yeah.
And the benefits are they're the biggest in aluminum, because aluminum, you're typically not limited by surface speed.
Right.
You know, there's really no such thing as tool wear with carbide tools or PCD tools in aluminum. So the faster you can go, typically you can enter into these bigger and bigger sections of the white, stability lobe diagram, where you can not only get rid of chatter, but maximize your material. You're not suffering. There's very few instances in life where there's no trade-offs. But with this, going at a higher spindle speed allows you to feed faster.
Yeah. Going
at a higher spindle speed allows you to cut more in your axial depth of cut. So it's a win-win for manufacturers.
Yeah. Big gains to be had in aluminum for sure. So this is one big way that industry is using or analyzing and measuring natural frequencies.
Yes.
And using that to improve. There's another one, and one example from the same company.
Yes.
Their product called the harmonizer.
Yes.
Can you explain what's going on here?
So this uses acoustical signals, and it analyzes those acoustical signals. So just like when a machinist hears a cut and says, you're chattering, that's not good, we need to fix some things.
Yeah.
He knows based on the sound what a good stable cut sounds like and what a bad chatter cut sounds like. Well, you need that person there who knows the differences in those two sounds to tell you if you're chattering or not.
Yeah.
This tool helps quantify that so that the computer can say, yes, we've analyzed the acoustical signal and you are chattering. So not only does it detect that you are chattering, this will recommend a new spindle speed to try in order to reach, or in order to get to a stable machining.
Yeah, and you can see the screenshot here. It's got these different frequencies it's picking up on,
right,
and it's trying to match those. So you're going to tell it some of the information about your process, and it's going to spit out after listening to the process. You have to actually run the process in the chatter condition.
Correct.
And record it, and it'll tell you what frequencies are available, and it'll suggest an RPM to match those things up for you.
Yes, it does all the analysis for you, because, I'm not able to do that kind of math in my head, but the computer can. So, the computer does the math and then it suggests the spindle speed that you should try. And it is sometimes an iterative process. You may have to try one or two different speeds, but it will eventually get you to spindle speed.
Yeah, so if you've got chatter that's not destroying immediately, you can survive a couple cuts. This is a pretty quick tool.
Yes.
It's just listening, just need a microphone and a little bit of software.
Yes.
So at this point, we've covered a lot of the basics about regeneration of weightiness.
Yes.
Type of chatter. And we're going to throw out now some rules of thumb that people will often say if someone's encountering chatter. And we're going to hold it up to our truthiness meter.
Okay.
So I'm gonna give you these, and as the viewers watching, based off of what you've just seen so far, as we've talked about where chatter comes from, I want you to see what you think of these comments and what's your reaction, and kind of walk through those with us. So the first one, and this was one of the first things I heard as an applications engineer, is if you're getting chatter, increase your feed rate. How does that one hit you?
That's not an all-encompassing statement. You need more information to be able to
maybe jumping the gun on that.
Yes, right. I would gather more information before I, told somebody. You can't use it as a blanket statement that applies to every situation. Yeah. With every tool, the tool manufacturer is going to have a recommended feed per tooth value.
Right.
This statement applies for people who are feeding too low, outside of the manufacturer's, and not only outside, but on the low end of the manufacturer's tool. So for a tool, let's say a solid carbide half inch end mill, in aluminum, the manufacturer is going to recommend something between 3,000 and 12,000 per tooth, somewhere in that range. Every manufacturer is different. Follow their recommendation. So this phrase, if you're getting chatter, increase your feed rate, that only applies if you're feeding well below the manufacturer's recommended chip load. So if you're feeding it half a thou per tooth or 12 microns per tooth, that's probably inappropriate. And this would be the answer for that. But it's not. As a general, it's not the answer to eliminating chatter. Yeah. Chatter can exist even when you're in an appropriate feed range.
Yeah. And we grabbed a couple of pictures here from some older type manual equipment.
Yes.
And then we're just guessing, but we're thinking this may have come up here where you're on a machine and you're just kind of babying a cut into something. You got to make one part, you're getting it through, and you could be getting chatter just because you're not pushing on it. You're just not aggressively engaging the material enough to create a thick chip.
Right.
You spend a lot of time rubbing. And this can happen anytime someone's, a little bit tentative about machine. They could just get this squealing, as we talked about up front. We got quite a bit of chatter from running real low chip thickness. But we also talked about within the regeneration of weightiness, your chip thickness is proportional to how much cutting force is being observed by the cutter. And if you are having a chatter situation and you increase the chip thickness, you could be just elevating, making the situation worse, adding more force, or adding more load to something that's already varying wildly. So could actually be more, which was the situation I had years ago with someone who does this. That's why I remember that quote so well. It did not work.
Right.
So, the next one, you need to properly load the machine.
Yeah. So again, I think this one came from the manual machining days. I can't be positive because I wasn't.
We weren't there.
Yeah, I was there. But I think it came from the manual machining days, saying, for this particular lathe here, there's nothing holding the bed or the slide down except gravity. So you always want the forces, the cutting forces that you generate while turning, to be in the down direction. Yeah. So you're always pushing the table or the slide onto the table.
Right.
So, maybe that's where it came from. I'm not really sure, but it doesn't really have a lot of meaning with modern CNC machines.
Right. In the modern CNC world, everything's pretty well tightly assembled. That machine should be able to take cuts of any magnitude in any direction, essentially within the limits of the machine.
Yes, within the limits of the machine.
We're not talking about a machine where maybe you've got a ball nut that's a little bit loose, and you just need to make sure you're keeping those cutting forces going in a certain direction.
Right.
That should not be a concern. If that is a concern, Makino has some great machines that we can recommend for you.
Lots of solutions to that problem.
So, moving on to the next one, truthiness. People say when you're having chatter, shorten your tool. Shorter is always better.
99% of the time, that is absolutely true.
Okay, that's a good one we can hold on to.
Yes.
Yeah.
Yes. Now, whatever feature you make, your tool needs to be long enough to create whatever feature you're trying to create. But your tool shouldn't be much longer than, and by longer, I'm sorry, we mean to stick out what we've shown here in the picture. So the 1 inch to stick out and the 2 inches to stick out and the 3 inches to stick out. That's this half-inch tool that we have here. As long as you can create the feature, you want that tool as short as possible because the shorter the tool, the stiffer the tool. And stiffness, the stiffer the tool, the more material you can remove stably.
Yeah. So when you talked about regeneration of waviness, a stiffer tool, the waves that it's creating are simply going to be smaller.
Yes.
It's not much motion there.
Correct.
So that you're going to get closer and closer to that ideal chip shape.
Yes.
As you have a stiffer tool.
Yes.
And it's really impacted quite heavily by the length.
Yes.
And so I brought up this example again, which even though it has that rigid wall on the diagram, which we decided we can't use that word, but this is that formula we had before you get your eyes glazed over. We're just going to focus on one part of that formula, which is the length part, and how that relates to the deflection.
Yes.
And within that, we're kind of thinking, the deflection is kind of proportional to that length, and that length has a cube on it.
Yes.
And so, real basic math, but we just wanted to cover, just make sure everyone's, got this in their frame of mind when they're selecting tools, that has a humongous impact on the stiffness.
Yes.
Actually, the deflection. So let's say you had just a unit of 1 on the length and a unit of 1 on the deflection. We use that as our baseline. Let's say you increase the length by 25%, like what you have here, a length of 1.25. We've now increased that. We've doubled. We've gone to 1.95, that level of deflection.
Right.
Just by 25%.
Yeah.
So you can think, if you're getting some chatter and you've got 1 inch of clearance, the thing to do might be just loosen that collet and pull it back half an inch,
Right.
If you double the tool length, it's not double the deflection. I mean, that's the key thing. It's 8 times the deflection. Now, the key difference here is you were clear to point out to me this is static situation, right? And we're talking dynamic.
Yes, but the similar trend, the pattern still follows.
Yeah.
So these, we chose these to help simplify things. This is the static deflection equation. What we mean by static is the force is constant and it's just staying there.
Yeah.
In milling, the forces are constantly changing, and it's also that force is changing with time. It's not just constant force. So, but if we try to pick something that everybody has hopefully seen before, and then say this idea absolutely applies to dynamic.
Yeah, in a practical way.
Yes, as well. So the longer the tool, the less stiff the tool.
Yeah. And now there's some changes there as we shorten so we get better stiffness. We also we've changed that system. So now the natural frequencies can be different.
Correct.
And you've got some pretty cool data to show us here. It can be a little overwhelming.
Yeah.
So don't worry, he's going to walk us through what's happening here and what he's got plotted out. But still in the idea of what happens when we shorten or adjust the length of our tools.
Yeah, so what this graph shows us, this is the same half-inch tool, but at different stick-out lengths. So you see we start at the left side, L equals 5.5. That means the stick-out length is 5.5 inches, and this is for a half-inch tool. So each of those colors is a different tool stick-out length, and then we measured the tool's dynamics at that stick-out length. So what the horizontal axis represents is the frequency, the natural frequency of the tool as a function of stick-out length, because each color is a different stick-out length. And then what that left side represents is, let's think of it as the tool's stiffness. So the taller that peak is, the less stiff the tool is. Mm-hmm. So in general, to help us understand and crunch this information, a smaller peak is better.
Yeah.
That's what we want.
Yeah.
And so it shows how both the stiffness changes and the natural frequency changes of a half-inch tool as we go from a 5.5-inch stick out on the left side all the way down to a 1-inch stick out on the right side. So we span a difference. We start at a 5.5-inch stick out. We're somewhere in the neighborhood of 450 hertz natural frequency, all the way up to a 1700 hertz natural frequency, or 1750 at a 1-inch stick out. Yeah. So your stick out can greatly influence what spindle speed you select, as well as the stiffness of your tool, which goes right into how do you best maximize material removal rate. And so, you can't just say this tool can remove this because they're this much, because you need to know what the tool's doing, and it's strongly dependent on the stick out length of the tool. So we've shown 3 pictures here to kind of give you an idea of what it looks like. So the 3-inch stick out tool is that little green peak. You see it has a natural frequency of around 1100 hertz. Yeah. A 2-inch stick out half-inch tool is somewhere around 1500 hertz natural frequency, and then the 1-inch tool has a natural frequency of somewhere around 1750.
So that frequency is going to directly impact that wave that we're creating on the chip, that regeneration wave.
Yes, and what spindle speed you need to select for the different stick out.
Yeah. So I think this illustrates very well how essentially the deflection per given force just drops dramatically as we get shorter.
Yeah. So
the stiffness is illustrated there. And then we introduced this idea of how it also changes the natural frequency of the system. And that's why at the beginning when I said shorter always better, you said, 99% of the time.
Yeah.
And we had to qualify that because we're pretty sure that there's someone out there who's going to raise their hand and say, hey, I saw this one time.
The 1%.
Yeah, we saw where the tool worked better when it was long. And so you searched through your database and you found a situation where this could be true.
Right.
So I'll let you walk through a little bit here. Here we say short is always better, but in this case, it's going to be, with a caveat.
Right. The small footnote, the very fine print is, if you're choosing between a 5.5-inch stick out and a 1-inch stick out, yes, the 1-inch stick out is better as long as you can make the feature that you're trying to make. But sometimes, let's say we have a 4-inch stick out, and let's say we're using a machine that has a 20,000 RPM spindle. So if we tap the tool and we get the top stability lobe diagram for a 4-inch stick out tool, we can see that we can cut at 20,000 RPM, and our axial depth of cut is about 2 millimeters before we start chattering.
Yeah.
It'd be nice if we could go to 22,000 RPM, because then we could get a little bit higher, maybe 2.5, but we're limited by our spindle speed of our machine. Exactly, that's all you got. So by lengthening the tool and to 4.5 inches, that's not a significant decrease in stiffness of 4.5-inch stick out compared to a 4-inch stick out. Right. So you're sacrificing a little bit of stiffness, but what happens is, because the relationship, the natural frequency of the tool also shifts, it aligns better with the 20,000 RPM spindle.
Yeah.
So for the 4.5-inch stick out tool, everything else held constant, that peak aligns very well with the 20,000 RPM spindle, and so you're not only able to cut at 20,000 RPM and cut it 3.5-inch or 3.5 millimeter depth of cut, instead of before where it was shorter, and shorter is always better, right?
Yeah.
In a very small and very select situation, is that statement not true? But 99% of the time, make your tool as short as you can.
Yeah. So, if you have a vibrations expert, there may be some opportunities to find when it's longer. Otherwise, it could be a lot of guess and check.
Yes.
There's a lot of red on this graph.
Right.
trying to find those white spots by adjusting your tool length and moving the dials up and down. It can take a long time.
Yes, absolutely.
So along with this idea, we've really been focusing on chatter as it relates to the tool in a situation about like this. So we've got this big heavy block, and we've got a tool, and so we're saying, okay, you're hitting chatter. We're assuming it's the tool moving around. But when you create an extreme situation like this, where now we've got a very thin wall, if we were getting chatter in this situation, I would look at that and tell someone that, hey, the wall is moving.
Right.
So they're getting chatter from the part movement. Do they still do a tap test, or how do you still monkey with the RPM? How do you address that type of chatter situation?
So, as you're absolutely correct, the less stiff element, or the least stiff element, is your limiting factor.
Okay.
So, just from, eyeballing this, we can pretty safely guess that tool is much stiffer than that thin wall right there.
Yeah.
So, instead, so most of the deflection is happening on the part side, or that thin wall side. So, instead of selecting a spindle speed to match the vibration of your tool, the tool is not really what's moving around that much. The tool is vibrating.
Yeah.
As we said, nothing's rigid. But it's really that wall that's doing most of the moving around. So what you want to do is measure the dynamics of that wall or the part and select spindle speeds that coincide with the wall's natural frequency.
Okay.
And now we've chosen this extreme example. There's better ways to machine this feature right here.
Right.
Thin wall machining is very well developed, and there's better strategies to create this thin wall here. We're not trying to say make a thin wall like this.
Yeah.
But we're trying to introduce the idea of sometimes it is the part that is the most flexible or least stiff element in your machining process, and measuring your tool's natural frequency and trying to select a good spindle speed based on your tool wouldn't help you in this case, because it's actually the part or the work piece that is the most flexible. So you want to measure the part and then select the spindle speed based on the part's dynamics, because everything vibrates when you input energy, and the least stiff element is the one that you want to match.
Yeah, and you had a great example just in the last couple of weeks where you were measuring various components and people were getting some chatter on the process. People wonder where it's coming from. And you measured the tool and you measured the fixturing, and you said the fixturing was 1,000 times stiffer than the tool.
Yes.
And so you were quite certain that it is a tool that is deflecting,
Yes.
not the fixture.
Correct. Correct.
So some of those measurements can be very helpful in a situation like that, because vibration is often a unknown realm for a lot of people.
Yeah.
So we're hoping to give you guys some tools to go into a conversation, but also understand that people you're talking to probably don't have an understanding of this,
right?
Because it is just not well understood,
right?
And also within this, you had a great example come up recently where the part was deflecting, or was the most flexible element. I like that way. The most flexible was the part, and you see in red here we had on this particular process some very aggressive chatter marks on the rim of this part. So it was a form tool milling around the rim of this part and leaving these chatter marks, and you were able to correct that.
Yes.
What did you do here?
So the first thing I did was I looked at both the workpiece and the tool. The tool was a 2 or 2.5 inch diameter form tool that stuck out maybe an inch. So fairly stiff tool. And I looked at the part, and it's sticking out. But, it goes ding, exactly. So I recognized right away that it's probably the tool that is the most flexible element.
Or most stiff. The tool is most stiff.
The tool is the most stiff. I'm sorry, the part is the most flexible. So I measured the part's dynamics with the Metal Max kit to determine what spindle speeds we should be cutting at. And for this particular example, we measured it, and then we found a good spindle speed that not only gave us a good surface finish, a stable cut, but it also, we were able to cut a higher RPM, so it increased or decreased the cycle time of this part. So it was absolutely a win-win. The spindle speed had to be properly selected, but it actually increased from what they were originally machining at. Yeah. And it gave a fantastic surface finish. So the next picture that we have shows with just a change of spindle speed. So by properly selecting a spindle speed, you can increase productivity and, let's say, eliminate chatter or find stable,
an acceptable finish.
Spindle speed.
Yeah. Yes. So this was one of those great situations where, because it was aluminum, you're able to go faster.
Yes.
And it was stable. And that's one of those things where it would have been very difficult because you did change the chip thickness a little bit and things, and it would have been difficult to kind of guess your way to that final solution.
Right.
So we're about to wrap up, but I want to review a few things. We talked about regeneration of waviness.
Yes.
And in this situation, it was the motion of the least stiff element, which was the motion of the part that was creating those waves.
Yes.
You're with correct form. And we do that by matching that with the tooth pass frequency. If you can measure, you can look at the stability load diagram that we talked about earlier. And it's all about looking at what's the least stiff element and matching to that frequency. But there's also this whole idea that you can also have machine structures that vibrate and move. And we've decided not to cover that because we're out of time and it's a whole other subject, right?
It really is.
But the bottom line of that topic is that you want to get the stiffest machine possible.
Yes.
If you're having machine structure vibrations, that's very challenging to overcome. And at Makino, one of the things that's great about here is that we don't run into it at times because we do have very stiff platforms. And that comes from a whole world, a realm of decisions, from the front of the spindle bearing down the shaft to the linear guides and ball screws that drive the y-axis in this machine, to the column shape, the bed shape, the guides on the other axes, the table, all the bearings involved there. Like each one of these is designed to be very, very stiff. We choose large sizes within the world of linear guides. There's a whole realm within a same style of guide. You can pick 25 millimeter, 35, 45, 55. And Makino invests a lot of money in these larger components, not just because they last longer, can take higher loads, but because they are stiffer and improve performance. And that stiffness translates into what you see on the stability load diagrams. We're pushing those axial depths up. We're widening the places where you can find a stable machine. We're also improving the service life of those components, so it's a win-win for customers. And that translates right into lower maintenance costs of machines and also lower consumable costs because you're shipping your tools less. When they're deflecting a smaller amount, they're more likely to be in a stable condition and a more even level of loading. But that's a whole other topic. If you're having machine structure issues, that's another thing that Makino can certainly help you with. And at that, we're ready to take some questions. I believe we had some come in while we were talking.
Cool. Yeah, gentlemen, thank you very much. We definitely have a couple of minutes left for questions, and we definitely have a couple of questions. So I'm just going to dive right in and pick one. How does an unequally spaced tool affect the calculation for tool hertz and also the stability lobes from the tap test?
So I'm not aware of the software being able to account for unequally spaced teeth. That unequally spaced teeth, I believe, came from tool manufacturers trying to create a one-size-fits-all tool. So with regeneration of waviness, if you have equally spaced teeth, the wave regeneration happens because they are equally spaced. By making a tool with unequally spaced teeth, you're interrupting that regeneration of that waviness, so you in a sense, break up the regeneration of waviness, but those, in my experience, have not led to significant increases in productivity. It's better to buy equally spaced teeth and just measure the tool and run it at a good spindle speed rather than trying to fiddle around with teeth spacing and that sort of thing. I believe, and again, I'm not positive, but I believe it's tool manufacturers that try to make a one-size-fits-all tool, and by changing the tooth spacing, it's able to perform a little bit better at all spindle speeds rather than having fixed tooth spacing and finding good spindle speeds.
So especially in the realm of aluminum, where you can get the big lobes. Now, I've used some of these tools before and had pretty good success in the hard metals, where you have very low, narrow range of speed.
Yes.
That can be very helpful.
Absolutely.
In those areas. That's interesting. I hadn't really thought about it in the realm of what it's doing through the regeneration of weightiness. It's
yes.
Just kind of slicing
it's
off
breaking
that.
that up.
Yeah. Oh, that's interesting.
Okay, I'm going to speak in one more here. We're a little over time, but I think this is a good one to end on. How do you know if chatter is from the tool or from the machine structure?
So, in general, what I would say is do a gut check. If you have a 1/4-inch tool sticking out of let's say a Cat 40 taper, it's probably not the machine shaking around. If you have and I'm doing extremes, obviously, to help illustrate what I'm talking about. If you have a 6-inch face mill and a Cat 40 taper, at that point, machine structure could be what's happening, because your tool stiffness is approaching the column stiffness. So just as we discussed, measuring, you can measure the tool stiffness. You can also measure the structure stiffness. So by measuring both of those elements, you can see, it's actually the machine that we are exciting instead of just the tool. Because if you measure the tool's stiffness with the Metal Max kit or the tap testing kit, and then you measure the columns stiffness, and it gives you a similar stiffness, that tells you that you are exciting your machine structure because your tool isn't any less stiff than your column. So that can, in general, you can do kind of a gut check. If it's a real small tool, it's probably the tool that's chattering. But once you get bigger and bigger tools, that's when it becomes possible to be exciting the machine structure instead of the tool. And at that point, you would just want to measure the tool and measure the structure, and then determine based on those measurements what's happening, whether it's the tool or it's the structure.
At that point, that's a pretty advanced set of measurements.
That really is, yeah.
Typically, you said look for that least stiff element.
Right.
So if you've got a thin tool in there, it makes the decision easy. If you've got a real big tool in there, you could be setting the whole system.
Right.
No.
Excellent. All right, we're about 3 minutes past, but I think it was well worth it. A lot of tremendous information communicated today. Before we sign off, I want to thank both of you, as well as, of course, Makino, for presenting during today's webinar. And I want to remind all the attendees that the webcast on demand version will be available on the Aviation Week website within the next 48 hours or so, and will remain available for 1 year. If you registered for the webinar, you will get an email alerting you when the on-demand version is ready. On behalf of Makino, as well as Aviation Week Network, I want to thank you for participating in today's event. Have a wonderful remainder of your day.